Now let us look at switching. And switching is a very important aspect of our data communication and networking. So why do we require switch or switching? We have certain type of switching like first is you have telephone network. So when you make a call, you talk to a person. So there is a dedicated line, and when this is a dedicated line, this is known as circuit switching. This is known as circuit switching. So for circuit switching, this is required that there should be a connection, a dedicated connection. It needs to be established between two parties, sender and the receiver. So this is a switched network. Switched. So see in detail that a switched network can be circuit switched. It can be packet switched. Most important is the example of internet, packet switched network. Then the message switch network. So in this packet switch networks, it can be divided into the datagram networks and virtual circuit networks. This is the whole taxonomy of your switched networks, and we'll see why our switching is necessary. Why would we require switching? And what are these different networks which are named as circuit switched, packet switched, and message switch network? And we'll also see the categorization of our packet switch networks, that is datagram networks and virtual circuit networks. We'll start with the circuit switch networks. So a circuit switch network consists of set of switches connected by a physical links. A network is known as circuit switch network, which consists of set of switches connected by a physical links. And the connection between two stations is a dedicated path. This is very important. It is a dedicated path made of one or more links. So there has to be a dedicated path between the TX and RX, that is transmitter and receiver. However, each connection uses only one dedicated channel on each link. So each link is normally divided into n channels by using FDM or TDM, that is frequency division multiplexing or time division multiplexing. So we'll see the three phases: efficiency, delay, and circuit switch telephony in telephone networks. A circuit switch network is made up of links connected by physical links, in which each link is divided into n channels. This is a trivial circuit switch network. Here we want to send data or send a signal from A to B. So these are the dedicated links or switches in between, and this is the dedicated path or connection between A and M, and we have one link with n channels. What do we mean when we say one link with n channels? That means if a link is there, there will be for one link there can be n channels, or we'll see it in quite detail. In circuit switching, the resources need to be reserved during the setup phase. Why I am pressurizing or emphasizing the connected or the dedicated setup is this: the resources need to be reserved during the setup phase. So if A needs to talk to B, then there has to be a dedicated network employing the resources which are needed to be reserved. And these resources, they remain dedicated for the entire duration of data transfer until the tear down phase. So what this implies is even if the sender or receiver, they are not talking, A or B, they are not talking, but still the connection is established, the link will be always, or the resources will always be, say, occupied between A and B. These resources are being occupied even if there is no talk, or even if they are not talking. Even if I've just made a call and the B has received, and we are not talking, but the call is still there. then the resources will always be there. Means you cannot employ this line for any other purpose. See, as a trivial example, let us use a circuit switch network to connect 8 telephones in a small area. So communication is through say 4 kilohertz, 4 kilohertz voice channels. And we assume that each link uses say frequency division multiplexing to connect a maximum of 2 voice channels. The bandwidth of each link is then how much? 4 kilohertz, 1 voice channel. So as I said, n channels. So for 2 voice channels, it will be 4 into 2, that is 8 kilohertz. So we'll see a figure which shows this situation. And telephone 1 is connected to telephone 7, 2 to 5, 3 to 8, 4 to 6. Of course, the situation may change when new connections are made. And the switch controls the connections. How it is going to be? This is a circuit switch network. And the bandwidth of the channel is for 1 is 4 kilohertz. But when these are the switches. So when the communication is on, both would require how much? 0 to 8. That is, if there are 2 channels, it will be 2 into 4 kilohertz. It will be 8 kilohertz. And 1, as I said, 1 is connected to say 7 or 8. And again, this 3 is connected to 7 or 8. Likewise, 3 and 4, they are connected to 5 and 6. As another example, we consider a circuit switch network that connects computer in 2 remote offices of a private company. The offices are connected using say T1 line leads for communication service provider. So there are 4 into 8 switches, 4 inputs, 8 outputs in this network. And for each switch, 4 output ports are folded into the input ports to allow the communication between computers in the same office. And 4 other output ports, they allow communication between the 2 offices. So this is the situation of circuit switch network. In this, we have 4 systems here, 4 systems here. So this is 4 into 8 switch. And what it means is it is employed the T1 line of say 1.544 megabit per second. And these are 4 lines and 4 into 8 switches, which means there are 4 into 8, that is 4 inputs and 8 output switches in the network. And for each switch, 4 output ports are folded into the input ports to allow communication between computer in the same office. That means if I want to talk to you, I need to use these folded input. So this is 4 into 8 switch, which makes possible for these 4 to communicate with these 4, along with these 4 to talk with themselves in between. There is a delay in a circuit switch network. What will be the delay? There is a time to connect. That means when A wants to connect to B, then there is a setup time or connection time. Say a ring goes. If a ring goes and you pick up. This is the connection time for this. Now start sending the data. And there is a time for disconnection also. This is the disconnection time. So for each, we have a total delay of this much amount. That means because they are switch network, there will be a delay in your circuit switch network. So switching at the physical layer in the traditional telephone network, it uses the circuit switching approach. So just assume, if you are not able to understand in any case, the way your telephone network works, it is an example of your circuit switching approach. Then we have datagram networks. In data communication, we would like to send messages from one end system or from one point to another. If the message is going to pass through a packet switch network, it needs to be divided into packets or fixed or variable size. So the size of the packet is determined by the network and the governing protocol. In a circuit switching network, what happens? If, say, we have to talk, then we need how many n channels? If n people are talking, we need n connections are to establish. We need n channels. Now these n channels, when I'm talking to somebody, that channel is always there with the increased bandwidth of n. So there is requirement of always larger bandwidth for this communication, and also a connection needs to be established. So the better idea is to send it in packets, different packets, and send them. Say this is 1, this is 2, this is 3. So send them. It may happen that 2 may follow some other path, 3 may follow some other path, 1 may follow some other path. But these 1, 2, 3 will ultimately reach to the destination because of the information which is there of the destination. And then these packets can be combined. So if the message is going to pass through packet switch network, which I'm talking about here right now, it needs to be divided into packets of fixed or variable size. So the size of the packet is determined by the network and the governing protocol. So see the routing table, the efficiency, the delay, and datagram networks in the network or internet. In packet switch network, there is no resource reservation. You don't require a dedicated line. If these are the various networks available, it can take any path from one point to another. The packet can take any path, and you don't require to have a dedicated network or dedicated path. So there is no resource allocation, and the resources are allocated on demand. So you don't require n channels also. So there is a huge improvement in the efficiency. This is a simple datagram network with 4 switches. These are our data, or packets to be more precise. And we have 4 routers here. As you can see, that my one will take this path, then this path, then this one, and it reaches to the destination. While the second, this packet may take this path and reach. And it is not necessary that this packet will take this path only. It can always take this path, say this path. So it depends on the 4 switches or the routers in between, which decide that which path needs to be taken or which is the free path, which is the shortest path. The routing table which decides or which tells where to go or which the switch decides that 1 has to go here, 4 has to go here, 2 has to go here, and 3 has to take this path. So the destination address and the output port in the packet will decide where the datagram has to actually go. So these are the destination address and these are the output ports. So this address and port, they in combined way, every switch or the router will decide that this packet is destined for this destination address and this output port. The output port 1 has a destination address of 1232. This third has output port destination address of 9130. So a switch in a datagram network uses a routing table that you have just seen that is based on the destination address. This address, destination address. And the destination address in the header of a packet. So a packet is consists of various information. One of the information is the destination address, which makes it possible for all the packets, though they take any path, to reach the exact same destination for whom it was sent. So the destination address in the header of a packet in the datagram network remains the same during the entire journey of the packet. Though the physical addresses like the routers and the switches in between, they may change, but the destination address would never change. This is the delay in the datagram network. This is the total delay. So what happens that the transmission time, this may be the transmission time, and the packets may have to wait till the time this switch or a router decides which packet needs to be sent where, because this may have various packets at its disposal to decide which packet has to go where. So this is the waiting time. Again, some certain waiting time for this switch. So ultimately it reaches here, and this is always the time for transmission. The transmission time along with the waiting time is the delay time in the datagram network. The switching in the internet is done by using the datagram approach, that is the packet approach, to packet switching at the network layer. So network layer does play a very important role in this packet switching, and you so say switch work on this layer only. Then above this layer we have transport layer, which deals with the TCP and IP, which is actual datagram transfer that can use your TCP, that is the reliable connection oriented, or UDP, unreliable connectionless. These are the datagrams. Then we have virtual circuit networks. So virtual circuit network is a cross between your circuit switch network and a datagram network. The datagram network is packet switch network. So it has some characteristics of both of this. We'll see the different parts of virtual circuit networks. This is a virtual circuit network, and for the system, it do have switches. It would require somewhere the dedicated path, but somewhere it may use the packet switching. So that is a blend of these two, virtual circuit network. This is the virtual circuit identifier, because if you have a data, you actually need VCI, that is virtual circuit identifier, and this again has some VCI. These are the switches in between. So a data or the packet, it passes through switch, and this VCI changes until it reaches the exact destination. So the switches and tables in a virtual circuit network would be like this. For an incoming, this is say incoming. For port 1, this is port 1. The VCI could be, or the virtual circuit is 77. For this data, it will be 14. And for outgoing, this data, that is reassign the value of 22, which goes or which takes the path, and this second one takes this path. See, VCIs are changing, virtual circuit. These are the source to destination data transfer in a virtual circuit network. So what happens here, what is happening here is, from A to B, there is certain destination. In between, you have a WAN, that is a wide area network. And you know, wide area network may connect two systems or 2 points, 2 nodes, and across 2 countries also. Wide area network. In this, the data which is coming to the port 1, which is having a VCI of 14, and it find its path through the port 3 like this. Now this data has 66 VCI. And when it reaches this switch, in this input it will be 66, but when it goes out, when it is assigned the outgoing VCI, it will be say 22. And when it reaches here, this 22 will be reassigned, or the VCI of 77. So it will reach B. So ultimately A reaches B through this path, employing the source to destination data transfer using these virtual circuit networks. And this is the setup request in a virtual circuit network which is required. What it does here is in the beginning, when the transfer take place, say this is A. So when it because the incoming is 14, there is no VCI assigned. But for port 3, when it goes, again VCI is not assigned. It goes to 3, no VCI assigned. And now VCI is 77. Now these values will be assigned here, as it has just asked for the setup in a virtual circuit network. So before any communication can commence, there is a setup request in a virtual circuit network like this. And there will be, once this setup has been asked for, there is a setup acknowledgement. Now you see all these have, or these connection has been assigned, because as we said, virtual circuit network, it is a blend of circuit switching as well as the packet switching. So now you have these VCIs, now the communication can commence. So in a virtual circuit switching, all packets belonging to the same source and destination travel the same path, that is the circuit switching. But the packets may arrive at the destination with different delays if resource allocation is on demand. If resource is scarce, then there is no problem because resources are allocated as per requirement and they arrive at the destination with different delays. And you have known the delay. So this is the delay in virtual circuit network. This is the setup time, as we have just seen. This is the setup time. This is for transmission, and this is for tear down or the closing of the established sequence. So switching at data link layer that is this layer 2 in a switch WAN is normally implemented by using the virtual circuit techniques, WAN, wide area network. What is the structure of a switch? We use switches in circuit switched and packet switched networks. So we'll see the structures of the switches which are used in each type of network. We'll see the structure of circuit switches, then the structure of packet switches. So this switch, this is a crossbar switch with 3 inputs and 4 outputs. So these are 3 inputs and see these are 4 outputs, and we call it as a cross point. And this is the connection. See, this can be connected, this can be disconnected to the control station. This is a crossbar switch. This is the multi-stage switch. Multi-stage switch means you have, say, N, capital N input. The output is also capital N. But if this N, these are small n's, they combine to form capital N. So these are crossbars, as we have just seen. So there will be N input and K output. So there will be K crossbars in between, that is N by N into capital N by N at stage 2. And then again this N into K will become K into N crossbars. So we'll finally get the number of outputs as was in the input. So these are multi-stage switches. So in a 3-stage switch, the total number of cross points will be 2 into K into capital N plus K capital N by N whole square, which is much smaller than the number of cross points in a single stage switch. So this multi-staging is just to reduce, or the resource, that is the number of cross points required, is much less than the actual N square. N input, N output. We don't require that N square. We will go for the 3-stage switch that will require only this much of cross points. To design a 3-stage 200 by 200 switch, that is N equal to 200, 200 input, 200 output, with K equal to 4 and N equal to 20, and we have just seen the formula. So if in the first stage we have capital N by N, or 10 crossbars, say 200 by 20, how much is this? 10 crossbars. Each of size, how much? 20 into 4, that is this 20 N into K. In the second stage we have 4 crossbars, each of size this 10 into 10. In the third stage we have 10 crossbars, which is K into N, that is 4 into 20. 4 into 20. 4 into 20. So the total number of cross points will be 2 into K into capital N plus K capital N by N whole square, or it will be 2000 cross points, which is only 5% of the total number of cross points. If we do N square, that is 200 and 200, in a single stage we would require 40,000 cross points. So according to the close criterion, N is equal to N by 2 to the power half, that is root N by 2. If K is greater than 2n minus 1, the cross point will always be greater than or equal to 4n bracket 2n, that is under root 2n minus 1. So we will redesign the previous 3-stage 200 by 200 switch using the close criteria with minimum number of cross points. So we know that N equal to what? Under root of N by 2. So 200 by 2, this is 200. Capital N by 2 under root, that is 10. So we calculate K, which is equal to 2n minus 1, that is 19. So in first stage, how much we need? 200 by 10, that is 20 crossbars, each with 10 into this 10 N into K, that is 10 into 19 cross points. The second stage we have 19 crossbars with each 10 by 10 cross points. Third stage we have 20 crossbars with K into N, that is 19 into 10 cross points. So the total number of cross points will be 20 into 10 into 20, 19, 19 into 20 into 20, and plus 20 into 19 into 10. That is 15,200. This is the time slot interchange. What it means is, this is a time division switch. This is using the time division multiplexing. So this A, B, C, D, when it is sent, this is sequentially controlled, and then with the control unit, say 1 to 3, 2 to 4, 3 to 1, or 4 to 2, this is selectively controlled here. And then this DCBA may reach as BADC, but it will reach to the destination where it is intended. So TSI, that is time slot interchange, will introduce various processing delays. See what processing is going on. So this TST, time space time switch, is with respect to time and with respect to space. There are three levels: time, space, and time. So these are crossbars, and these are TSI. So there are three level: time, space, time switch. And with packet switch components, for the input ports, for packet we ought to know the input and output ports. So we have a routing processor and a switching fabric, which for the input ports decides the output ports. In this input port we have a physical layer processor, also the layer 2, that is layer 1, layer 2 processor. Then we have a queue which queues the data packets. And in the output port again we have a queue which gets the data. We have layer 2 processor and layer 1 processor. This is a Banyan switch. N input, and then with N input we have, say, left bit as 0, this is left bit, this is the middle bit, and this is the right bit. Say 0 0 0 for 0, and then for 1 we have 0 0 1. Say for 7, what it will be? It will be 1 2 and 4. So 1 1 1 1 1 1. So these are the left bit, middle bit, right bit for sending, say, 0 to 7. So how many are these? 8. The stages would be log base of 2n. These are 8. Place it here. That will be 3 stages. 1 2 3. And if you want, say, if just consider it is 4 stages. What it means? 4 bits. So what it will be? 2 to the power 4. So we can have 16 inputs. So this is the input 1 sending a cell to output 6. 1 sending the output 6. You know what 6 is? 0 1 1 6. And here input 5 is sending what? 0 1 0, that is 2. This is example of routing in a Banyan switch. This is Batcher Banyan switch. So along with the Banyan switch, we have batch switcher and a trap module, which makes a Batcher Banyan switch. So these were three concepts of your switching. So you really need to learn this Frozon book, which has given more examples and exemplified, and this is described in more detail there. But you might have got a glimpse of what exactly this switching means. Thank you so much.